The hash calculation function GHASH is defined in Chapter 6.4 of the NIST publication and specified as pseudocode in Algorithm 2. GHASH hashes a multiple of 128-bit input given in X into a 128-bit output by multiplying each 128-bit chunk of X with a power of the 128-bit constant H and XORing all the multiplications together. Within GCM, GHASH is used to calculate the pre-counter for the counter mode-based encryption of the plaintext into the ciphertext and is also used for the calculation of the hash value, capturing the authentication of the ciphertext coupled with the associated data. The counter mode-based encryption function GCTR is defined in Chapter 6.5 of the NIST publication and specified as pseudocode in Algorithm 3. GCTR encrypts the data provided in variable X by repeatedly incrementing a 32-bit counter and encrypting this counter with the underlying block cipher. The result of this encryption is then XORed with the 128-bit chunks of the data provided in X. The concatenation of the results of these XORs then gives the overall ciphertext. In GCM, the G-counter calculation is used to calculate the ciphertext as well as to encrypt the hash value representing the authentication of the ciphertext coupled with the associated data. Having established a basic understanding of the workings of the GHASH and the G-counter functions, it's time to get into the demo of how I implemented these functions in Python. Going into the implementation of GHASH as defined by Algorithm 2 in Chapter 6.4 of the NIST specification, Step 1 was to split the input X into 128-bit blocks. Step 2 was to prepare the 128-bit 0 block Y0. Step 3 was then the loop multiplying the XORs of the input 128-bit blocks with the 128-bit constant H. The XOR of byte strings and the multiplication of 128-bit blocks I delegated to two yet to be implemented functions. And with step 3 completed, all that was left was step 4, which was to return the 128-bit result of the final multiplication as the resulting hash of X. The multiplication of 128-bit blocks was more involved and as an operation is defined in Algorithm 1 in Chapter 6.3 of the NIST publication. First, I turned the 128-bit blocks represented as byte strings into integers in order to ease the implementation of the subsequent bit operations. The first step of the actual algorithm was then to extract the bits of X, which I extracted into variables small x. Step 2 I then combined with step 3, where in step 3 a loop over each of the 128 bits of X takes place, where first Z is updated depending on the current bit of X, and where second V is updated depending on its current state. Once this loop finishes, the result of the multiplication of the 128 bit blocks X and Y are captured in Z, which in step 4 I then returned as a 128-bit byte string. At this point missing was the definition of the constant R, which is defined on the first line in chapter 6.3. At this point, I realized that the loop was missing the updating of the state variables zi and vi, which I added accordingly. Implementing the XOR of byte strings was a short function to write, and I did this, as I did in previous demos, by zipping the bytes of the byte strings together and XORing each pair of bytes into a new byte string. With GHASH done, I then proceeded to implement the GCTR encryption function as specified in algorithm 3 of chapter 6.5. Step 1 was to simply check if the input X to encrypt is the empty string, and if so, to return the empty string as the ciphertext. Step 2 then asked to extract the number of 128 bit blocks in the input X into n. Step 3 then splits the input X into 128 bit blocks and possibly a last partial block with less than 128 bits. Steps 4 and 5 then define the n counters required for the subsequent encryption, where each counter in the list is the increment of the previous counter. At this stage, I still left the increment function as a function left to be implemented shortly, and proceeded to implement steps 6 and 7, combined, where all the counters are encrypted with AES, and the result of the encryption XORed with the 128 bit blocks of the input X. The last block of X may be partial, but this is appropriately handled by the XOR bytes function, only XORing bytes as long as both byte strings have bytes to provide. Step 8 then asked to concatenate all previous XORs of steps 7 and 8 together into Y, with Y in step 9 then returned as the result of the GCTR encryption of X. The last function left to implement was the 32-bit counter increment function, which is defined in Chapter 6.2 of the NIST publication and which considers the rightmost 32 bits of the argument y as the fields for the counter. To implement this increment, I first turned the argument y into an integer, then deleted the rightmost 32 bits, and set the rightmost 32 bits to a value incremented by 1 from the previous value. The resulting integer value I then returned as a 128-bit byte string. With this increment function implemented, I headed back to the driver with the 3 NIST-based test vectors, and running the program then indicated that the implementation indeed is a correct implementation of GCM with AES as the underlying block cipher, at least with respect to the 3 test vectors provided. This was quite cool to see, even though I knew that in order to fully validate the implementation would need to pass all the test vectors provided by NIST.